Hello, can you hear me?
Yes, yes, madam.
Okay. Let me
Shall we proceed?
switch on the camera and it's I'm trying to upload. Just hold on. Uh, can I share my screen?
Yes, ma'am, you can share.
Okay, let me share my screen. Just hold on. I think there is a problem. Okay. Sorry, I have to log out and log in back because
Yes.
there is a problem.
Yes, ma'am. Yes, ma'am.
Yeah. Let me. Yeah.
Rejoin.
Sure. Thank you. Yeah. Thank you.
So, good morning, participants. Welcome for the first session of the third day. There is some technical issue, so that's why it is getting delayed. I hope it will be resolved soon, and we will start the first session. Ma'am, your mic is off.
Can you see my screen?
No, madam.
Can you see my screen?
No.
No?
Yeah. Ma'am, there is the Pageant Now button you have seen?
No?
At the
No.
below, there is the Pageant Now button just beside the right side of the hand. Hand is showing raise hand option and then the Pageant Now option.
Hand. But yeah, it is. Yeah, I know that.
Yes,
Yeah, no,
yes.
that's
Now,
yeah.
now,
You
now it
can
is
see my
set.
screen now.
Now it is visible. Now it is visible.
Yeah.
It takes some time.
Okay. Thank
Now
you.
it's visible. So,
Yeah, exactly.
ma'am, it's okay now. We may proceed.
Just 1 minute. What do you see on the screen? Because I don't think the transitions are visible.
It's showing Bitcoin
Do you
mining.
see my transitions?
Bitcoin mining.
Okay. Yeah. Can you see my first slide?
Yes.
Now I think it should be okay. Okay.
Okay. So, ma'am, shall I start?
Yeah, sure. Thank you.
Okay. So, good morning, participants. On behalf of the Department of Computer Science and Engineering, National Institute of Technology, Sikkim, it is my privilege and pleasure to welcome Dr. Sushmita Roos Madam from University of New South Wales, Sydney, Australia, in this session to deliver an expert lecture on blockchains through a cryptographic lens. Dr. Sushmita Roos Madam is a senior research scientist in CSIRO Data 61. She is also a conjoint associate professor at the School of Computer Science and Engineering, University of New South Wales, Sydney. Her primary research interests are in applied cryptography, cybersecurity, blockchains, and data privacy. She designed practical, efficient, and probably secure protocols that can be deployed in real-life applications. Her interests are in critical infrastructure, including smart grid and cloud, ad hoc networks, and data sharing frameworks. Her aim is carry out impactful research by bridging the gap between theory and practice. She actively collaborates with the government, academia, and industry, and this has made research a very enriching experience for her. She has collaborated with researchers across 5 continents and has delivered over 80 technical lectures around the world. She is a senior member of ACM and IEEE. Prior to joining CSIRO, she spent 7 years in academia as a faculty and then assistant professor at Indian Institute of Technology, Indore, and then as assistant professor and later as associate professor at Indian Statistical Institute, Kolkata. During her stay in ISI Kolkata, she led a flourishing team of masters, PhD, and postdoc. She has won several competitive grants like Samsung GRO Award, NET Faculty Fellowship, Cisco Academy Grant, and IBM Research OCSP Grant. She has published more than 130 publications, and her research articles are well recognized by the eminent scientists and researchers throughout the globe, and that achieves 4,260 citations till today, having H index 27 and I10 index 52. So thank you, madam, for spending your valuable time with us. We hope that your session will be really enjoyable and interactive with our participants. So now I request you to deliver your lecture. Over to you, madam.
Thank you very much for the kind introduction, and thanks to all the organizers and Dr. Roy for this opportunity and inviting me to this um, faculty development program. So what I'm going to do first is to take you through, give you a very high-level overview of blockchains and the type of cryptographic techniques we use. So I honestly cannot see my audience, so which is actually a big problem for my talks. But I'm not very sure how much of blockchain is known to the audience. So what I'm going to do is start from the very basics, and then give some idea of the type of research that is going on in a particular direction. So blockchain has now become uh, very broad, very vast, with lots of research directions in either in security, privacy, as well as networks. Um, different people look at it in different ways, from the distributed computing angle, from the economic perspectives, and even from law and governance. So such an is an area where a number of um, disciplines are engaged. Researchers of number of disciplines, not just researchers, practitioners, I would also say, are engaged from different disciplines, and this makes it very enriching domain. And what I'm going to do now is just tell you a little bit of history about blockchains, because blockchain to a lot of people means something new, but for many of us who were in um, who have been doing cryptography, have known many of these techniques or many of the building blocks, and have been using these building blocks for a very long time. So if you notice the history, you would see that hash functions, digital signatures, they came long back in 1975. One of the earlier works of the Byzantine general's problem, which is one of the foundational stepping stone in blockchains, as I will be discussing later, also has a long history in the 1970s, late 70s. And the very interesting phenomena that happened, or very um, interesting piece of work, was secure timestamping. And this essentially would was one of the stepping stones of blockchains, I would say. 85 DigiCash was introduced, which is nothing but digital currency, and this was there for quite some time. One of the building blocks in many blockchain technologies is the proof of work, uh, which is which was introduced in 1992 by Cynthia Dwork. Now, and this was not just that at that point of time there was no cryptocurrency. It was not even used for this purpose. It was actually to figure out, or it was used for spam detection, and not just spam detection, but also protection against spam. And later there were a number of following DigiCash, there were eGold, and the number of precursors of cryptocurrencies that were introduced much earlier. And one of the secure timestamping protocol evolved into surety, which is which was very interesting phenomena. And they did surety did secure timestamping, and they would publish this timestamp in the newspaper, which is actually widely circulated around the globe, and it made important. It was one of the earlier works of this blockchain phenomena, I would say. Very interestingly, Bitcoin, which is a very popular blockchain protocol, I would say, emerged in 2008. And it was, many people think that it was not just by luck, but it was just after the financial crisis of 2008. At that point of time, there were a lot of Lehman Brothers, and there was a need for centralized authority, financial authority, and Bitcoin was very timely placed, and in this whole scheme of things, and became very rapidly was taken up very rapidly, and has seen enormous growth in the recent years. It has also seen a lot of fluctuations. It has seen a lot of growth and a lot of use. And blockchain, when we talk of blockchain, it means so many things, but it started with the Bitcoin. The term came with Bitcoin, but it was there in various guises much earlier than Bitcoin, which was which was proposed in 2008 in a seminal paper by Satoshi Nakamoto. And the very interesting part of the story is that no one till date knows who is this person. They only are aware that there's such a technical paper that was written, and it all started a very big revolution, um, which is now, I mean, almost 13 years now. A lot of diversification in terms of, it started with a cryptocurrency, the Bitcoin cryptocurrency, but now blockchains are no longer just cryptocurrencies. They mean a lot of things, and has been used in a number of application, starting from insurance, finance, that were traditional use, to a number of applications such as supply chain, then Internet of Things, and a number of other applications that we will see during the course of the. So maybe what I can do is that, if you have any questions, I'm not being able to see the screen and not being able to read the chat. Uh, what I would suggest that, someone reads it out for me, and don't wait till the end of the talk. Please ask questions as we go, so that it's much easier to clarify and move forward in this, and that way things will be much easier.
Ma'am, they can directly unmute themselves and ask question.
Yes, that will be really nice. Yeah, that would be great. Yeah. Please unmute yourself and ask questions. So, I always give this example, which is something that is my example. I've not seen it anywhere else. In the rest of the things would be, I will not discuss much of my research, but also most of the work is what I have read and what I've seen. But this example is unique, and so I always try to give this example to explain what blockchain is. And this is an example from in the mythological story of Chitragupta, who who is believed to maintain a large ledger, where all human activities are noted down in a chronological order, and it is believed that to punish a person or reward a person is decided based upon what is written in this ledger, or a big notebook that we typically have heard in our mythological stories. And if you just think back and observe that, over here the whole trust is on a central party, or one person who is Chitragupta, and this person is prone to make mistakes. This person might not be able to record all that is happening around, and even a slightest mistake would mean that, I have done a good job, but it was not noted, or maybe I've done a bad job and it was not noted, and I should have been punished, where I was, I did not, I got scot free. So it all depends upon this trust on Chitragupta, and that is how we have assumed that Chitragupta is all trusted, and we have assumed that all these decisions have been recorded properly in a proper chronological order. And so think of any system, if it is centralized in nature, it is prone to failure. It could be prone to failure. It could be prone to malicious action, and that is why if we think of multiple Chitraguptas instead of one, then it makes things much easier. So if instead of one Chitragupta, there were, multiple Chitraguptas sitting there and noting down our actions, then, or everyone colluding together to punish a person for good things might not have happened, and any one mistake would have been, not everyone would make the same mistake of noting activities in the ledger. So, moving from centralized to the decentralized system would essentially make it more, prevent central point of failure in the whole scheme of things. Now, notice that there are a couple of issues over here that we need to address. So, one of the things that this notebook is maintained by multiple people and think with each other. So it's not that some people write certain parts of the story and certain parts of her action, and some part people don't do that. So all the notebooks of of say 100 or 1,000 Chitraguptas should be in sync with one another, and that is something that we need to have. That first of all, there is replicated, so the ledgers are replicated, and it is maintained by multiple parties, and the ledgers should be in sync with each other. So that is a very important thing. Now, note one thing is that all the entries that are in the ledger, they should be proper, in the sense that read something, erase a particular entry from the ledger, uh, erased by everyone else in the network, or everyone, all the Chitraguptas together. And it becomes very difficult, because that means that the coordinated effort between all malicious and faulty Chitraguptas have to be in sync, which is a very difficult task. So two things are very important. One of them is to ensure that the records are not manipulated. Once written, they are there. So it means that it is a permanent record. It is not changeable or immutable. This ledger is immutable, and you could only append to this ledger. You cannot delete anything. You cannot modify anything. You can simply append to this ledger. So this ledger will grow from with time to time, as time goes by. All the people who are maintaining these ledgers should be in sync with one another, and those are exactly what the blockchain does. So the blockchain essentially maintains ledgers which are immutable. It is shared amongst and replicated and maintained by multiple parties, and they are verifiable in some way. There would be, all these Chitraguptas should be able to verify that this action had taken place in some way. These are some of the concerns that needs to be addressed in the blockchain setting, and exactly these mean that there are three very important problems that need to be addressed in the blockchain. These three integral concepts are that of a distributed ledger, meaning that you have multiple Chitraguptas maintaining the same copy of ledger, that no one can tamper with the records that are already written in the ledger, and these are only append only. This is an append only ledger, and consensus, meaning that everyone should come to one viewpoint as what is to be written in the ledger. So two Chitraguptas cannot have two different views of the ledger. They should actually come in sync with one another. So this is exactly what blockchain does, and there are different ways to realize it. So the main idea of blockchain is to have these three features, but only thing is that they realize it in different ways. They are represented in different ways. And most of you, if you have seen Bitcoin, you will see that this is a few blocks together combined in a straight line. And that becomes a blockchain. So that is how the Bitcoin looks like. There are many other blockchains which look very different which have a different structure. So irrespective irrespective of the structure, irrespective of the application, these are things that need to be complied with. And having these requirements, or having this set of concepts makes demands some requirements that needs to be fulfilled. The first is that of scalability. Because I'm writing, it's an only append only ledger. It means that I'm simply adding entries to this ledger. So it is going to become bigger and bigger and bigger. So what happens as the ledger grows in length? How do I manage it? Not just a ledger, physical ledger. It would have been a big notebook. You could actually think of it as a storage device. Now, the storage device, if I were maintaining multiple copies of the storage device and writing many things in the on the device, then it would become very, very long. So one question is that of scalability, not only in terms of storage, scalability in terms of storage, but also performance. And what does it mean? It means that if you have multiple Chitraguptas trying to be in sync with one another and trying to come into an agreement or a consensus, it means that they need to communicate with one another. So think of, say, two friends, they want to ensure that they are writing the same thing, they have to talk to one another. Now imagine that three friends are wanting to talk. So they have to, so A, B, C have to say that A has to send this message to B and C, B again has to send this message to A and B, and so on. So the problem is that as the number of peer nodes who are maintaining this ledger, or as the number of Chitraguptas increase in the network, actually means that they need to exchange a lot more messages for communicating their information. And this would essentially be a very big performance bottleneck. So how do we go around this problem of performance? The third question that comes with immutability. How do I ensure immutability in the ledger? What are the security requirements? How do I ensure that no one tampers with this information? So these are some of the requirements. Now, these are very generic requirements I'm talking about. Different blockchains would have very specific requirements that we will see later. These could be in terms of scalability, performance, or any other factor, security, privacy requirements. But these are something very generic to all blockchains that we have come across. In order to understand how to address these problems and satisfy all these requirements, we need a little bit of a background. So maybe I will pause here and ask the audience if they have any questions about the basic structure of blockchain. So I have not essentially talked about a structure or drew a structure, but the only motivation is that why do I need this blockchain, and how I might be able to why these requirements are there. So maybe just a few seconds and wait for 15 to 20 seconds if anyone has questions.
Sushmita ma'am, I have a question.
Yeah, sure.
Maybe I feel I park my question towards the end of this because it is more related to the security. I want to understand your presentation more, and then add this question.
Okay, yeah, sure.
Okay.
No worries.
I'm just giving you a heads up.
Fine. So then maybe I will proceed to say how these can be realized. And the first building block, I would say, is that of a hash function. And a hash function is a function which maps into which takes in a string of random length. And here I am using a string of zeros and ones. It could be it is a function that maps a variable length string into a fixed length string, say of length L. And what I'd say is that this is a fixed length string, which is called a digest of the message, which is a variable length string. There are a few requirements of this hash function, and the first requirement is that it is very easy to compute. So h is a hash function, so given a message m, it is very easy to compute hm. It is the other way around is difficult. So given hm, it is very difficult to compute m. So x, it's not x given is equal to hm, it is very difficult to compute m. So there is a mistake over here in this case. And so this is called the one-wayness of the function. And the other couple of requirements is that if you have, say, message digest x, it is very difficult to find another message digest which will I think I've messed up with this notation. So if you have one message digest, say xm and hm, x is equal to hm, and you have another message digest hm dashed, it will be very difficult to find the same they are mapping to the same x. So this is one requirement. And the other thing is that given it is very difficult to find two messages, m and m dashed, which will again map to the same thing. With these notations or these requirements, there are traditionally, long list of functions that you can consider, and different functions are used for different blockchains. For example, SHA-256 is used in Bitcoin. And what does this mean? What is the significance of having this hash function? That I'm going to tell in the next couple of slides. So apart from hash function, the other important tool that we need is digital signatures. And just like a normal signature, in a normal signature, the signer signs a document, and either a designated verifier or a public verifier can verify a signature. It is just the same over here. Here, instead of we have a digital document, so it is signed by some secret information of the user. So over here, if you look at this SA, just hold on. Just maybe try to get my let me see how to hold on. How do I use the pen here?
Ma'am,
No.
ma'am, on
Let
the
me, yeah.
the right
Let
down
me do it this way, then it's easier. Yeah, please tell me.
on the right down corner,
Write down.
there is three shapes, right? One rectangle and circle and triangle, right? Click on that. Over there, you will find out whiteboarding.
Which one? Hold on. Which place will I go? Oh, okay.
Right
Got
down
it.
corner, right?
Got
Over
it.
there, whiteboarding would be there.
Yeah, whiteboard. Yeah, whiteboard. Whiteboard. No, not this. There's a whiteboard here. What I'm going to do is that I'll just make it a little bigger. This pen over here, or maybe just the cursor over here. It's much easier. Thank you very much. Okay, so of this Alice has a document and it has to sign with certain it has to sign this document, and it uses a secret information which is known only to Alice, and this is called the signing key. And Alice signs this secret information. Alice signs this document using the secret information, and sends this to Bob. And what Bob does, so this is a signed message, which is which is signed message, which is a sigma, which is the signature on the message, and Bob does uses a verification key, which is a public information. So the PKA is a public key, which is verification key for Bob, and it verifies the message the PKA. So the verify function should not only contain sigma but also the message as well as public information of Alice to verify that this message signature pair is a valid one. And the important thing is that the adversary, even if the adversary sees multiple signature pairs, it will not be able to generate a new message signature, valid message signature pair on a new message signature pair. So the digital signatures are very important because they tell us that what is the origin of this transaction, what is the origin of this this action that has taken place. Because if someone is making a transaction, be it a financial transaction or something else, it has to say that I have made this transaction. It has I have created the transaction, and in order to say this, it says that I'm signing this transaction, and this signature is unforgeable, meaning that no one will be able to create a signature on a message. And it is not on that message alone. It cannot create a signature which will look like it's coming from Alice on a different message as well. So that is the type of guarantee that these digital signatures give. So what the blockchain, the way blockchains are realized is various types of blockchains. So this is one of the earliest representation that is there in Bitcoin. But please make a note that this is not the only representation of a blockchain. I give it because of the simplicity of explanation. But there are various types of blockchains which have different representations, not just this one. So note that now I will just move from that example of Chitragupta writing our actions to say financial transactions. It is much easier to give this example. So in a financial transaction, let us say that Alice wants to send some money to Bob. So that is a one transaction, for example. So what happens is that in a blockchain, function is that you have to guarantee that there is an immutability in this blockchain. So it essentially means that once written, cannot be altered. Immutability. So how does Bitcoin blockchain do it? And many of the other blockchain follow a similar structure. So the way they do it is that they club together multiple transactions and to make a Merkle tree out of it. The very interesting property of the Merkle tree that I'm going to talk about later is that Merkle tree is created such that if one of these transactions get invalidated, then this information, which I call the TX root, is invalidated. So you have to, you cannot essentially able to generate another transaction TX2 dashed, which will again have the transaction root to be the same as before. And the reason you cannot do it will be coming from the because of the hash function that I'm going to talk in the next slide. But before that, let me tell you that the blockchain essentially takes many transactions together and creates a hash of the transactions and puts it as a TX root. And it also keeps the hash of the previous block. What it means is that if this block is tampered, then this ph, the hash of this message, the hash of this block has to be changed. Now, imagine that if this block is, for example, corrupted, it means that all the subsequent blocks in the blockchain have to be changed. And in doing that, what it means is that this blockchain is maintained as the same copy is replicated along many nodes in the network. So if one node just changes one block, it has to change all subsequent blocks, not only in its own blockchain, but nodes have to be have to follow the same thing. So they also have to change all the blocks, all the blocks starting from with this block in all the subsequent in all the nodes. And now imagine if the majority of honest nodes in the network, they would not be able to do, they would not do that, because it's, and if there is one or two corrupted nodes, or maybe majority of non-majority of nodes who are corrupted, then still there would be a majority of nodes who are non-corrupted, and they would essentially maintain this blockchain intact. Two things become very clear, that this hash function, the property of hash function is such that you will not be able to know what is there in the previous block. So that is why you cannot even another hash that will map to the same thing. And also the property, as I mentioned, that it is very difficult to find another block which will have the same hash value. So that is where the property of the hash function comes into account, why we need the hash function in this case. So this is one thing. So this immutability is ensured using these hash functions and this Merkle tree. Stamp which it, and there is a random nonce, or a random number, which is called a nonce. So nonce essentially is going to be a unique number, and the reason it is used will become clear as I move on to the next few slides. This is how the blockchain looks like, and the Merkle tree now is nothing but a binary tree, and which a very nice property, which is called an authenticated binary tree. And the way it is constructed is that you have this information in the leaf nodes, and you compute the hash of these messages. Say if M1, M2, M3, and M8 are the leaves, then you compute the hash of M1, M2, M8, and then you take two blocks together and compute the hash of this, and so on. Interesting part of this entire process is that when you I have when you tamper, you have to tamper all the other blocks, because if one blocks get tampered, then if this block C gets tampered, then this block J gets tampered, and if J gets tampered, then M gets tampered. If M gets tampered, then the hash value at the root gets tampered. So going back over here, if TX1 gets tampered, then 01 gets tampered, root gets tampered. So the root value does not match with the thing earlier on. So that is why these Merkle trees are so beautiful, and in many, not most, I would say, I mean, in many blockchains, to ensure that the transactions are clubbed together properly, and none of the transactions are now. The next part of the thing that I talked about was this nonce. And nonce has a very interesting role to play, especially in the Bitcoin setting, and blockchains would have different sort of randomness involved. I'm doing this for Bitcoin because it's different. So this nonce is essentially, you think of it, think of again going back to the blockchain design. Now, questions come into picture because this is one blockchain and everyone has the same copy of the blockchain. There are a couple of questions that people might ask, is that who creates the block, and why will they at all create a block? Why will I create a block means I need to get some incentive to create a block, and that is why this question comes: what sort of incentives will I pay for generating a block? And this process should be a competitive process. Like if I were to give incentives to everyone, then it's very hard to how will I give that incentive? So it seems that I have to generate these incentives also to pay it to the different parties who are generating the blocks. So that is why Bitcoin took a very nice, interesting perspective, and it's called a Bitcoin mining. So what they did was that not just having a set of valid transactions clubbed together in the TX root, a puzzle, meaning that you have done some amount of work. You are getting a reward because you have done some work. And that is called a proof of work. So the reward is somehow proportional to the amount of work that you have performed in some way. So what it means is that you have to do this work. You cannot actually generate and this work is in terms of a puzzle. So that you have to solve a puzzle. In order to solve the puzzle, you have to work. It's not that it's very easy to guess the solution of the puzzle. If it were very easy to guess the solution of the puzzle, then many people would have been able to guess it. So the trick over here is that in order to solve the puzzle, you simply have to do multiple times to be able to know the answer of the solution. And this is called a proof of work. And in the case of Bitcoin, the way it does is that you take the hash of the block that you have generated and you compute and you check whether it is less than some pre-defined value z. If it is so, then you give it as you say that this, I have found the golden block and I'm going to broadcast it to everyone. But it's not very easy process. It's not very easy because the hash function generates a very random value, and it's very unlikely that it will be less than this difficulty level z that is set by the system. So what the miners do is that they change the nonce. They keep, because these values are the same, the timestamp would be a little bit different, but this nonce is changing from time to time. It's just they increase the set of the value of nonce, and they check this whether it's less than this value z, and so it computes many hash functions, and this is the proof of work that Bitcoin essentially does. The verification, on the other hand, is very easy because if I check, compute the h, and I will verify whether it is less than this value z. So verification is very fast, but generating a valid block is very hard because you cannot actually predict the value of the hash function. And you just have to check with nonce one after the other in order to generate a valid block. So this all depends upon now how quickly or how difficult it is to generate. So for example, if I were to choose this value to be, say, the z value according the z value in some way, then I might need a few hashes, but if I change the z value, I might have to do multiple hashes. And this is what is called the difficulty level, and the way it is set is using various parameters that I'm not going to talk about, in such a way that the average time to solve a puzzle is around 10 minutes. So average time to solve a puzzle essentially also means that the average time to generate a block is 10 minutes in the case of Bitcoin. And why would someone compute all these values? What is the incentive? So as a form of incentive, Bitcoin gives some BTC for the miners who generate the blocks, so they are called miners. And the way it works is that every time this 12.5 BTCs are generated in the Bitcoin system, and this value goes on decreasing every 4 years by half. So 12.5, and the next cycle it would be 6.25, and then after 4 years it will be 6.25 by 4. So this is how this entire mining process goes on. And note that in order to get this incentive, the miners have to compute hash functions multiple times, and this is a very interesting thing that was um, that essentially gives meaning that how many hashes do I compute per second. And in the Bitcoin system, it has been seen that the hash rate is terahashes. So, I mean, you will see that the estimated number of terahashes which was performed in the last 24 hours. So, if you see that, you know, how many terahashes are being computed is so big, so 140 180 million. So that's really very big number. And though the each hash function computation is very quick, so many hash computations, it's going to take a very long time. So the thing is that you waste a lot of energy just to compute these hash functions, and this is wasteful energy. So the proof of work that Bitcoin and many other cryptocurrencies, for example Monero and so on, they do is that it's very computation intensive. Now, just to give a little bit of background, this proof of works was proposed by Dwork and Noor to combat email spam, and later this was also adopted by Hashcash, which is another cryptocurrency, I would say digital currency, which also is a precursor. It's believed to be a precursor of the Bitcoin. The Bitcoin mining is very intensive, and so that's why there are special purpose, software, special purpose hardware to do these computing. And there are also a lot of supercomputers, mining farms that are involved in this game. Because it's not possible to do it on my machine or your machine or laptop or even our server and so on. So you need really big machines in order to be really lucky of mining this blocks. So uh, two things to note over here is I mentioned about coming together, and that's this is the block that we are this is a blockchain that we are looking at. Now imagine that there is a block like this over here, and there are two miners do it almost at the simultaneously, two blocks over here. So one miner creates one block on top of this, another miner creates another block on top of this. Now that's a big question to ask all the time. So now there might be some miners who might build on top of this, and there might be some miners who will build on top of this. So the way this Bitcoin actually chooses, so when this happens, this is called a fork. There is a branch, and this is called a fork. And so when forks happen, they have to be resolved, and Bitcoin takes the longest chain. So Ethereum, for example, Ethereum does a proof of work as well. Ethereum takes the heaviest chain, for example. So in taking the longest chain, so this is called a Nakamoto consensus. You would just drop in this part, this brown ones, which have become an orphaned block. The transactions often blocks have to wait to be included in a future block, maybe somewhere here or somewhere later. And these miners, so typically they say, you have to wait for some confirmation time, meaning that, if you have transactions here that are in this block, blocks to be built on top of this to get these transactions confirmed. And the reason is that it is possible that this transaction over here might have been dropped, because it might become orphan because there was a parallel chain over here, and that is why it takes some time to come to an agreement in the case of Bitcoin, and you have to wait to get your transaction confirmed. So that is again a big challenge in Bitcoin, and there are ways to get around this problem, and I'm not going to talk about it here. So note that over here, which chain is going to survive is again something that is not under anyone's control, and as long as 50% of the majority of there is honest majority in the network, this thing is going to work, and this will not result in any undesirable blockchain. So again, I mean, I'll take a pause over here because the next thing that I would like to mention goes a little bit about how transactions look like. And when I said that there is a need for signatures, I will say that what is the need for signatures. Okay, so and ask if anyone has questions or comments.
Yeah, ma'am, I have a question.
Please tell me.
Yeah.
Yeah.
I was just waiting for you to mention about the Bitcoin mining part. Yesterday we had a session on the security, the cyber security from the software and the hardware perspective. Using machine learning, cyber security, the robustness is getting increased. I mean, machine learning takes care of the cyber threats by learning and protecting the upcoming threats. So the discussion point yesterday was the doubt that I raised was in case if a hacker is trying to hack a machine learning piece of code which is built for security, there is a probability of cracking the code. Okay, there is a probability of the script which is written on machine learning. In case if I have to crack that code, there is the combination is in such a way that the probability, guessing the probability, it may take time. Okay, which is from my point of view. So is it similar to the Bitcoin miners who are working on the guessing this the code, right? Am I clear in? So there's a Bitcoin mining. A lot of people are trying to do the Bitcoin where some of them cracking it takes cracking the at least 15, 16 Bitcoins itself might take around 5-6 years of time for the processing before the computational time taken by the so-called the machines, the supercomputers to crack these codes.
So I'm not very sure what you mean by cracking the code. So over here, the main question is, can I generate a next block? So everyone is trying to generate the next block. So the supercomputers are being used to generate the next block.
Okay.
By solving that puzzle.
I think that's what I meant.
So it is going to take an enormous amount of time for normal machines because they cannot do it parallelly, but in supercomputers you could actually do it much faster, and how long it's going to take depending upon your computational resource. But note that you are trying to do one block and you have gathered a few transactions. By the time you generate your block, there might be another block which already has your transactions. So what are you going to do? Those transactions, it's kind of it will not be possible to put it in another. You have to put it in another block, and by the time you create another block, a much more powerful machine might have already done it. So that's a challenge here.
So from the security point of view, is it now? Can I take that this is the only technology which no cannot be hacked, or are there still threats to blockchain?
Yeah, there are many threats to the blockchain. I will say some of them in the talk now.
Okay.
Yeah, I think there is one question in chat as well. Which hash technique will be better to be implemented so that it will be applied in lightweight IoT? Okay. So there are different ways to use blockchain in IoT, and the to answer your question to ask um, is that what is it that you would need this blockchain for in the IoT scenario? Is it that you want to just validate that the messages coming out of the or being sent by the IoT device are authentic? And if you ask this question, I would ask, you can do it in any ways. Why do you need a blockchain? So it's a very interesting question, and I always tell anyone who is using a blockchain for any particular application is that just don't use that blockchain for that application unless until you can actually show that it is not possible to do without a blockchain. So my take on blockchain is that you need blockchain for something. Why you need the blockchain in the first place, not just because it's a fancy thing and everyone is using blockchain. That is a buzzword. I'm using blockchain also for my application, so please have a very strong case when you talk of blockchain in IoT or any other system. And I also see an IoT authentication. Sit, okay? Yeah, take some rest. Yeah, Daddy will give you. Yeah. Okay. Sorry about the interruption. Authentication. So again, the case has to be really clear that you at all need a blockchain in the first place, and there has to be a discussion as to what is meant by IoT authentication and why you cannot do it without a blockchain. So because you have messages coming out of IoT device in the first place, so you have to justify why blockchain has to come there. What is a unique point that a blockchain would bring into the table for IoT authentication? So this is something to ask. Start actually designing an IoT, lightweight IoT based blockchain application. So there is one question, nonce, how the nonce increasing the difficulty in the, okay. No, nonce is not increasing the difficulty in the system. So the difficulty is preset by the system. And this means that, just hold on. Now, how the nonce is not increasing the difficulty of the system. Nonce is only used to solve the puzzle by just it's increased every time by one, so that you compute the hash of one value with one particular nonce, change the nonce, compute the hash again. So these two are different disjoint things. The way the difficulty level is computed is by various other metric. And if you look into the Bitcoin wiki, you will find a very specific formula as how this difficulty level is adjusted according to time, according to the rate of mining, or rate of block generation, and the hash and the time period, and so on. So there are a lot of factors that are there in order to adjust the difficulty level. The nonce only is that you just have to compute it again and again and again. You could actually not use a nonce. You could just take a random value every time and just move, compute the hash and check with the difficulty level. Question, I see a hand up. Vikas, would you like to answer your question?
Yes, ma'am. I have a question about the solidity. Solidity language is used in blockchain. So, can you elaborate what is it and how we can learn it and how it is useful to generate a contract and other things?
Solidity is a contract, the smart contract. It's a language in which the smart contracts are written. So essentially, I have not yet talked about the of now, but I'm going to talk about the scripts in Bitcoin and say what is the correlation with smart contracts, and there I will mention about solidity. But it is just a language to start with, language in which, just like your other languages like C or something, it's not, don't draw parallels with C and solidity, but it's just another language. I'm going to talk about smart contracts, and I'm going to talk about.
There is a link between NFT and solidity or blockchain.
Between what?
NFT.
Between what?
NFT and solidity.
NFT. Okay. So NFT could be written in different things. I mean, so the programming language is dependent on the choice of the blockchain, which supports what language, and also you could have multiple blockchains supporting multiple languages, and so that is why you could have NFT making, you could have solidity or some other languages as well. So the language dependence comes from the programming aspect. When you want to represent a contract that it would support, use script which is not Turing complete. You cannot actually express many things in that language. Ethereum, on the other hand, uses solidity and so on. It has other support as well. So it tells you what are the how much it can support, or what the blockchain can support. So I hope that answers your question. So you could have a solidity or Rust or Go or whatever.
Ma'am, if a particular cryptocurrency is less crowded, can it be said that it is easier to mine? That is, it is less computation intensive. Like, for example, is it good to spend on the newer cryptocurrencies which have less coins in the market?
Okay, so that's a very interesting question. So there are a couple of things, and I think it's also an economic problem that you are mentioning. It's not just a technical problem. So, for example, the value of the cryptocurrency is also one of the motivating factors for people to mine. Always mining. Mining is a term that Bitcoin uses. There are other ways of generating blocks which are not even proof of work based blockchains. So in those cases, you have proof of stake or proof of burn or proof of authority or proof of elapsed time. There are many things that are used to achieve this consensus. Nakamoto consensus is a very loose consensus. It does not have any provable guarantees or anything. Whether it is easier to mine in a particular, or I would say not the mine, I would say generate blocks in a particular cryptocurrency, whether it is less crowded or not. There are two considerations. So if you ask people, it is something like, how much will I get if I generate a block? So for example, Bitcoin gives a huge amount of money. Another less known cryptocurrency might not even give you that amount of money to generate a block. You might be able to generate a block, but then you might get very, very less. The incentive is not as much like some of the other well-established blocks. And again, not all blockchains work in the same way as Bitcoin, like a proof of work. For example, in some cases, like proof of stake, you have to prove that you actually hold a big stake in order to be able to be the winner of the next block or be able to generator of the next block. So in that case, the nodes which have a higher stake have higher chances of success than nodes which do not have a higher chances of success, which is somewhat like rich getting richer phenomena. So I will not say directly that it's a very I would not assume that the less crowded ones would be much more easier to uh, yeah to mine or get more incentives from. So any more questions at this point? Okay, if not, then I'll move to the next part. Last few things about, because there were some questions about smart contracts and applications, I will move to that. Okay, so let me talk about let me talk about the smart contract first. And so let me show you how the transactions look like to start with, and then I will show what it means to have a smart contract. So if you look into the blockchain or the transactions, you will typically see something of this sort. Like you have an input and output. It could be multiple inputs, multiple outputs. It could be one input, two outputs, maybe 10 inputs, m inputs, n outputs, and so on. And this works is that you have to essentially there is what we call a list of so it is you have a wallet. So maybe I'll move to Bitcoin wallets first. So wallets are essentially where the Bitcoins are stored, or the cryptocurrencies are stored. And there is a list of unspent transactions, which is called the UTXO. So the first thing that happens is that it's a wallet is like your own wallet. Like if you ask for, you have to pay say 15 rupees, and then you either give 20 rupees, get 5 rupees back, or you can give 50 rupees, and then you can get say 20 rupees, 10 rupees, and 5 rupees back. So that is how you could actually give it. So you cannot actually take a 10 rupee coin, 20 rupee coin, and just tear it 3/4 and give it to the other person. So same way, the UTXO is list of unspent transaction. If you want to spend something, you have to take this. You have to check that this there in the list of unspent transaction in order to spend it. And in our wallets, it is something like that. In the Bitcoin wallets, in each of the Bitcoin wallets, is something like that. So the way this happens, every entity in the network, it has multiple addresses, and each address has a public key and a secret key information. This is how the transaction looks like. It has, say, for this particular transaction, it has one input, and with each input, it essentially tells us from which output it was generated. So input essentially means that there was you have taken it from the list of unspent transaction. So this means that previous output, and the way you essentially verify it, that you have a public key of the previous output, and you can essentially say that, look, I mean, I can spend it provided I have a particular signature on that. I can generate the signature for that particular input. So this is how these simple scripts look like. So they validate that I have a matching signature for the input that I have. So and note that this script, when I check the script, this is very simple check. It will first check whether the input sum is greater than the output sum, and the difference is a transaction fee. And the second condition is that the script sig, which is a part of the input, it has a valid signature on the transaction, and it's verified by the script's public key. So these two things should match together in order to make it usable, or maybe spendable, not usable but spendable. And these scripts are very simple scripts, and Bitcoin has only supports very few scripts. I'm not going to the details of the scripts, but to draw an analogy with the smart contracts, that Ethereum supports or many other blockchain supports are much stronger, or has a much more comprehensive. The reason Bitcoin went with this sort of an approach, is that it's much simpler to do frauds, and it could go wrong. In the case of, for example, smart contracts that are supported by other blockchains, there are ways and mechanisms to ensure that the smart contract is a valid smart contract in the first place, because there has been a lot of attacks on these smart contracts and how they work, which has actually had very catastrophic effects. So what I'm going to do at the end is give some idea of okay, let me about a couple of attacks, because I think someone mentioned about the maybe I should talk okay, since there was one question on whether, I mean, how I could profit from the mining, I would essentially suggest mention two things. Okay, so just before that, let's note on the Bitcoin scripts is that there are only few scripts that are supported by Bitcoin, and this is not Turing complete, meaning that it cannot handle loops or while statements for a big drawback for the Bitcoin scripts. And it also because it's very simple, it also is much more robust, I would say. And in order to have these proof of work, as I mentioned, that proof of work is wasteful, and it consumes a lot of computational power. So one of the things that have been proposed, as I mentioned, is that the proof of stake. Proof of stake essentially says that whoever has the highest stake would have a higher probability of generating the block. And there are various other proof of X, we call it, which are useful for various other, which are alternate ways to ensure consensus. So believed that the Bitcoin transactions are private, meaning that sender and receivers addresses are not known. And it is to some extent very true that the user in a wallet, having a wallet, could have multiple addresses and could generate multiple addresses. So it's very difficult to find out which Bitcoin belongs to whom, who has made this transaction, and people would think that this is highly anonymous transactions, but that is a myth. It has been seen that these transactions can be um, transactions can be traced, and you could actually get some idea of who made this transaction and how they made this transaction. Even though the privacy of Bitcoin is not guaranteed completely, um, there is something that essentially says that you could actually build on top of the Bitcoin some techniques that will guarantee the privacy. But those are again things that cryptographers do in order to hide the anonymity of the users and contribute to the privacy of the transaction. Now, one of the other questions that I think one of the other questions to ask is that how do I take into account the scaling issues in the Bitcoin? Because as long as Bitcoin or all other cryptocurrencies, scaling issue is a major issue because each block has a fixed length size, and you cannot just put in all transactions together. It will just create a bottleneck, and all nodes keep a copy of the entire blockchain. All the active nodes, or I would say the who are mining or who are full nodes, they call full nodes, they keep a copy of the blockchain. So it is very, this grows. It's not 80, it's much more than that now. It's a very heavy, a huge amount of storage that is there. So how do I take into account, or how do I scale this solution? So there is a lot of work that are being done on scaling blockchains, and some of the work that we have been doing recently with my PhD student are on scaling blockchains by using off-channel, off-the-chain mechanisms. So if you are looking for interesting problems, then there is one big issue is to look into the scaling issues of blockchain. Issue is that of how do I make these transactions really anonymous, and if you would like to have other privacy preserving protocols on top of a blockchain, existing blockchain, then how they would work. On the other hand, the other scaling issues is to have a very good consensus algorithms. So proof of stake, proof of storage, and alternates to the proof of work, which also does not consume as much energy. At the same time, they have some provable guarantees, unlike Bitcoin. So since I am, close to the time, I will one thing I would mention that there are a number of open questions or open challenges that are there in this domain, and word of caution everyone is that you know use blockchain use blockchain for applications where it is needed, because blockchain always adds another layer of overhead, because you have to write on the blockchain, you have to read from the blockchain, you have to communicate the transactions across the peer nodes. So it is always very expensive compared to a system without blockchain. So it's very important to see first why it is blockchain is needed in that particular application in order to use it. And so even if the case of IoT or supply chain, we ask this question, what is it? Do we need it? And all that I talked about so far was just permissionless blockchain, which means that anyone could join the system, anyone could leave the system, anyone could mine. However, there are more enterprise type of blockchains which are much more restrictive in nature. They would allow only certain nodes to participate as in the participation participate in the blockchain. And not just the realization in this talk for right. So what I'm going to do, I'm just switch to another. Maybe I'll just about smart contract the questions. So I'll just stop the slide share and I'll share something else. Okay. So this is a smart contract. So smart contract is less like any other contract. Think of a will or a property contract, and it is it has statements, and it is uh, there are certain statements that will trigger other actions that are trigger actions in the contract. The smart contracts that blockchains that the effectiveness of smart contracts in the case of blockchain is that the contract essentially verification is done on all the peer nodes. So it is not just verifying or the contract present in one node. It is actually executed. This contract is executed in all the peer nodes, which makes if the smart contract is not doing its task properly, it is tampered in one node, it cannot be tampered in all the other nodes. So that is one thing that you need to keep in mind. All the smart contract as a standalone smart contract, it just means that you have a sequence of statements and you're executing it in some way. On the other hand, and if you have some triggers, it will be the smart contract will be triggered, or smart contract will be executed in one way. The effectiveness of the blockchain is effectiveness of smart contracts in the blockchain is that the same piece of code, which is a contract, the code contract, it is present in all the code is present in all the nodes. So even there was one question: if there is is it tamper proof? Is it like resilient to attacks? Yes, in a way it is resilient as long as majority of the nodes are honest. So it means that if you change the code in one node, it is very difficult to change in all the nodes. So in that way, these contracts are properly executed. But there are is written in a way that can actually exploit the whole system, which has been done, then there is no way out. So writing proper smart contract is a very important thing, and it has to be taken into account that it is doing what it's supposed to do and not anything else. So maybe I will stop here, and we could actually take some questions if there are any. And in any case, if you have still questions, you could always email me, and we could I'll try to answer the questions. Okay, so any questions?
Any questions from participants?
Ma'am, can blockchain be used in transportation or international travel or domestic travel? So that, for example, we see that many of the people with criminal background, they relocate to another country. So if law and administration is combined with all these things, then it can be prevented with a blockchain application, so that at least they can be tracked and put to book. So is it possible? Is it a good solution for law and administration and as well as travel and all these things?
Yeah, so just keeping track of people would be nice. You could actually have the blockchain, but then there is a question keeping track of people. Like, for example, if I were to keep being kept track of my movements were being tracked and everyone could see the blockchain, I would think of it as a privacy violation. And so in designing such a thing, it's always a lot of things come into question, like what information will I store on the blockchain to ensure that I do not violate the individual's privacy. At the same time, I mean, it has to be properly coordinated and implemented in the sense that at the border control, you have to ensure that the correct information is written on the blockchain, and not everyone is able to see that information, and give permission only to certain set of individuals to see or track all this. But if you forget about blockchain in the first place, if you had a very solid, trusted setup with a trusted repository to maintain this information, um, then that would have been good enough. So if you are trying to design this application, you have to first justify that the existing system that is there, that typically you might not have essentially have this country-wise database, or databases being shared between two countries in terms of who goes in, who goes out, for example. But we honestly, I mean, you have to justify that at the first step, at the way things are done now. You have to find what is the way things are done now, and where it is lacking, or where you could actually find a loophole, or how can criminals be, you could actually track your criminals, um, but you would not compromise the other's individual privacy, or you would not you know falsely profile someone as a criminal. So all these things you have to take into consideration, see what are the current ways of doing it, what are the loopholes, and then go for the next step. What can blockchain do, how it can prevent that. So this is a question that is actually very true for all applications that you design on the blockchain. First, think of the application, how it is done in the normal scenario. Why is it not enough? Why is it lacking? What is it lacking? Why do I need a decentralized approach? Even if I decentralized approach, I mean, does it violate anything else? Or does it violate any other requirement that I have? So, I mean, for applications, it becomes very tricky, I would say. And so you could actually put anything on the blockchain. So it might be okay, but the question comes, why blockchain? And this has to be answered. Okay, so any more questions?
If you have any more questions, you may directly unmute yourself and ask question directly.
Okay, there is one question which is, and it's not a technical question, why most of government don't trust cryptocurrency blockchain and made it illegal. Okay, so that's a interesting question, and one of the reasons is that the volatility of this cryptocurrency. So it fluctuates very widely, and this could be really difficult to handle in an economy. So most governments are really skeptic about making it legal. The other thing is that there is a wide fear, which is believed because of some of the pseudonymity that these cryptocurrencies provide. That, for example, in the ransom, if people taking ransom, they're taking a ransom without understanding where it is coming from, who is asking for the ransom. So the question is, um, it is assumed that there are privacy issues, or sorry, not privacy, but anonymity issues in blockchains, and that is what makes governments a little bit also skeptical that the criminals might get off with it. So yeah. Any more questions? You could actually also email me if you have any.
So, ma'am, it looks like no more questions from the participants, and it was totally clear to all of them. So thank you, madam, for being with us in spite of your busy schedule. And I hope that we will get your continuous supports and your valuable time in near future too. so
Yeah,
that
sure.
the participants as well as the NIT students and teachers or NIT Sikkim fraternity will be benefited from this kind of sessions.
Yeah.
So thank you very much, madam, for being with us.
Thank you very much, and I hope I'll be able to meet all of you in person sometime.
Yes.
Thank you.
Whenever the
Bye.
pandemic situation is over, I hope that we may meet physically, either at
Yeah,
NIT
sure.
Sikkim or maybe at ISI Kolkata.
Thank you.
Thank
Take
you for a
care.
wonderful
Bye.
session, ma'am.
Thank you.
Thank you, ma'am.
Dear participants, one major announcement is there. Due to some technical issue, the second session of the day will start from 1:15 p.m. Okay, so you are requested to take your lunch and be joined within 1:10 p.m. So next session, that is the second session of this day, will start from 1:15 p.m. instead of 2 p.m. So please take your lunch and join within 1:10 p.m. Okay?
Okay, sir. Yeah.
Okay. So but you may logged in here, or you may go for lunch.
Okay, sir.